Okay, so you did about the same announcements as before. Working through your final project proposals, get you feedback on that. Otherwise, same deadlines and expectations as before. So, any questions? Otherwise, just keep plugging along. Um, yeah, so now we're kind of halfway through this the neural/learning unit. So last time we focused on ways in which we can use these connections of elements to classify patterns over time. And now we're focusing on this active process of gathering information as you move in space and then getting rewards from that information and learning something from that. In other words, reinforcement learning. And so the motivation here, I'm actually going to go back to swarm intelligence and ant colony optimization or ant system here. So and also mentioned that reinforcement learning. This falls. These learning categories we talk about in biology and psychology are not all inclusive. There's some that I have left out, but this reinforcement learning most strongly matches to an operant model where you're trying to encourage a behavior by giving rewards to that behavior after you've observed the behavior. So the rewards come after the behavior here. So that's why it's operant conditioning or trial and error learning. So, this is the idea that an agent is going to try something, get a reward from it, and that will change how likely it is for it to try that again. And we can focus on ant colonies as an example of this. And so we've got an ant nest on one side. We've got food sources on the other side, and they're going to be a large reward, a moderate reward, a small reward. And for simplicity, I'm not going to consider a giant network. I'm just going to say there's basically three paths here. You can go out the ant nest to the large reward, out the ant nest to the moderate reward, or out the ant nest to the small reward. So the idea here is that these different pathways are going to get reinforced with these pheromones. And so when an ant experiences the large reward, she will lay a larger pheromone trail on the path between the nest and that large reward. When she experiences the moderate reward, she'll lay a little less pheromone. When she receives the small reward, she'll receive a little less. And then those will get reinforced by others in her colony. So what we're actually seeing here is that over time, ants establish a network of trail pheromones that is a social memory. So these ants have an architecture to store reward information about past rewards, and estimates about where to find future rewards. And they store that in a network that is instantiated in chemicals in the environment. And that is what is going to be motivational for us as we think about this, especially as we think about the connections to neural networks. So something to keep in mind there. So the basic idea here is that when ants leave the nest, they then can experience all three of these four pheromone trails right at the nest. So when they're at the nest, there are these three trails that they can consider, and they have different amounts of pheromone. Initially, there's, before they've experienced these rewards, then they're all the same. At that point, an ant can just move randomly, and she can experience this, or this one with equal probability. So initially, she has no prior knowledge about where the reward is or what the reward distribution is shaped like. But over time, as she and her nestmates experience the rewards, then they reinforce these pathways so that in space, you get this memory of past rewards and prediction of future rewards. And then when an ant comes out and sees this social memory, she can now make a choice that is non-random, or that is according to a distribution that has less entropy than the initial distribution. So it has more order, has more predictability. She can leave this nest and maybe decide that it's more likely that she goes to the trail with a higher pheromone concentration. So we are going to refer to the nest where she's making that decision as the state where the decision is being made. And we're going to consider these three options as actions. So she'll take an action to choose one of these, and then she'll make that choice. But she could have, maybe it's more like she doesn't always take this choice. Maybe 95% of the time she takes this choice, 4% of the time this choice, and 1% of the time this choice. So there can be a distribution over these actions, but each individual action is just which long path did she take. So that's a lingo that we're going to use here, that the state is her position in space as she's making decisions. And for this very simple ant colony optimization, there's only one state. There's at the nest. So when you're at the nest, that's when you make the decision. And then there's 3 actions you can take at that particular state. Okay, so from there, the pheromone concentration in space, across this whole space, is the predicted quality of each action, starting from that given state. So that's what we're seeing in these pheromone concentrations. It's encoding a predicted quality. I'm using that term quality. It's not the best term, but it's the term we have. And this also might give you a hint as to where Q comes from in ant colony optimization. Quality. Quality, there's a maximal quality that can be out there, and you can modulate the predicted quality of these nests by the experience rewards. So the idea here is that we can model, we could draw this like this, but the same information could be modeled in a little function down here, where Q is the quality, S is the state. In this case, it's full of boring, it's always the nest, and A is the action, 1, 2, or 3. You go to nest 1, nest 2, or nest 3. And so initially, this quality estimate, there's no pheromones. So initially, this quality estimate has got an equal quality on all 3 actions. But as the ants experience the rewards and they start laying down pheromone, they are effectively creating, updating this function over time. So this is just a map of pheromones over space that is being updated by ants as they take actions and experience rewards. So, and then this is also updated by decay. So if ants don't reinforce these, so if maybe the ant comes out, she experiences a large reward, and then she reinforces this trail on her way back. If this reward goes away, then it stops getting reinforcement, and so then this decays over time. And so then that allows this quality function to then vary. It can go up, it can go down. So and if all the food sources go away, then it can just go back to all the actions having equal quality. So that's kind of the idea here. And then over time, what's going to happen is that you're going to get, if the rewards stay constant, then what you're going to get is more ants will collect at the large reward. Fewer ants will collect at the smaller reward, maybe a moderate amount of ants at the moderate reward. So ants explore by moving randomly, and then they gradually bias their exploration to start exploiting these pheromone concentrations. So initially, when there's no pheromone concentrations, the ants are exploring the space. And then eventually, as they get more information about the quality distribution, they start exploiting that information and effectively stop exploring and start just using this map of the quality functions and start exploiting the rewards rather than trying to find information. So initially they're starting and they're going, an equal number of ants are going to all 3 sites, even though they shouldn't spend much time here. Like it doesn't make a lot of sense. You don't get a lot of reward there, but they're information foraging initially. So, and as they get information, they build up this Q function. As they build up this Q function, they start to exploit the Q function so that eventually they effectively stop exploring and just start exploiting in proportion to the reward distribution. That's sort of the idea here. And so the individual decisions based on rewards lead to collective allocations that match down here. And so this is a psychological reference that match the reward distribution. So as we'll talk about a little bit later, there's these famous results in psychology where if you put a bird in a box or a human in the computer screen and you give them 2 levers to push, and this lever, every other time you push it, it gives you a peanut. and every 10th time you push this one, it gives you a peanut. It turns out that the bird will converge on pushing both levers, but it will spend more of its time pushing the one that's rewarded more frequently. And the balance of its time between the two levers will match the balance of the reward distributions. And that's the so-called matching law in psychology. And we get a colony level matching law here, where the foragers then adjust their distributions so that their collective foraging effort is biased should be shaped to match the reward distribution. That's our motivation. So any questions about this? So bringing swarm intelligence into the reinforcement learning. Okay. All right, so that's the picture. So let's formalize that a little bit more. And so this will be review for a lot of people, because I mean the boring thing about reinforcement learning is it's so old. It's hard sometimes to justify that it belongs when even talking about neural networks, except for one little wrinkle that I'll add that sort of is update to some of these things, so to speak, update to some of these ideas. But I mean, but reinforcement learning is much older than neural networks, and so you don't have to implement them with neural networks. It's just an old school machine learning approach, and consequently, I think more people have, there's oftentimes students have familiarity with some amount of RL, and so this ends up being a little bit of review, but I'll try to make it hopefully more interesting and take it to certain directions that hopefully you haven't seen before, hopefully. But so we have the state and the action, so the nest and the paths, and we're going to call that a state action pair. So at every state in your world, at every decision point in your world, you can take actions. So you can pair up where you were and what action you took. And that is your state action pair. And when taking action A, stuff happens. So when you decide to go down that path, you get a certain reward that you get to add to the amount of reward you've accumulated so far. And your state gets updated. The environment says, oh, you've taken that action, I'm going to move you to a new state. So you get moved from state S to state S prime. So now you're in a new state in the environment, and you potentially have a new distribution of rewards for actions at that new state. So the agent initially has no idea what the mapping from state action pairs to this quality function, like the accumulated value at each state action pair and the predicted value of the next actions. It doesn't know what that is. So as it's moving through the world, it has to do a combination of random exploration just to learn this function that we talked about in the previous one, this Q function. And then as it's exploring and it's learning about the quality, it then has to somehow switch or subtly move towards exploiting the information it's gathered and starting to take these high quality actions. This could be a robot moving through space. This could be a pharmaceutical trial. So it's initially, if you've got 3 different drugs that you're testing in a population and you don't know which one works best, you get 100 or 100,000 people to sign up for a trial, and you do this medical trial. And as you're going, you initially give a third of the people one drug, a third of people the other drug, a third of people the other drug. And as you keep going through the trial, you start noticing that one drug is giving you much better results than another. Now, you still need to learn about all this. You need to complete the study. But now that you've gained information that, it seems like it's beyond chance that this one drug has helped out this population, you now almost have a duty, especially if you're an MD, that you need to maximize the benefit that you're providing while also getting your study done. And so what sometimes will happen is when you start seeing very good results, then they may have a protocol which allows them to increase the number of people who are getting the drug that has favorable results. And so they still end up testing all 3 drugs, but they can change the distribution because they've gained enough information to know that we haven't quantified exactly what the effect size is, but we do know that this drug has an effect and it's stronger than these other drugs. So it would just not be responsible for us to continue to give everyone the same drug. We can actually crank this up so that we can still learn about the other drugs, but we can maximize the benefit we're providing during the trial. So that's an example of reinforcement learning happening at a human level in a very different application. So it could be, robots moving around a forest, or it could be doctors, research doctors, coming up with pharmaceutical tests. All right, so so what is a way to do this? Q learning is a staple of reinforcement learning to learn this quality function. So as mentioned in the ANT case, we have this function Q, quality, paired with the state action pair. It's the expected reward for doing action A in state S. And we have an exploration step, which takes the action A in state S, receives that reward, and then is moved from S to S prime, and then the agent updates this Q. And so how to update this Q as you're taking these exploration steps is an important thing. All right, so that's what we're going to talk about next, is update. Any questions about this layout, this formalism? Just taking our ANT example and then putting some numbers to it. Okay, so again, you start with exploration, probabilistic exploration. So there's different ways that you can explore based on the information you have from this Q function, which initially is no information. So one way to do that is a so-called epsilon greedy policy. And so in this case, you have this epsilon, and I'll say epsilon is epsilon is in 0 to 1. And it is typically small. So you have this small epsilon that you can choose, and then you pick the maximum for the given state. You look at your current quality, and you pick the action A that maximizes your current estimate of quality at this state with probability 1 minus epsilon. So most of the time, you take the quality maximizing action for this state. But for some epsilon probability, sometimes you just pick another one at random. And we definitely see this in ants. We definitely see that when ants are put in Y mazes in the lab, and you have a strong pheromone concentration on one side, you can watch every ant, and when they hit that fork, you can measure the probability that they're going to go left or right. And that and if the pheromone concentration is on one side and there's nothing on the other side, then you can see how many errors to make. What is their epsilon? And what's interesting is that ants that forage on ants species that tend to forage on things that are non-moving, that are dead, that are still going to be there time and time again, have a very low epsilon. They follow social information very well. If there's a strong pheromone trail, they just follow it. And those that forage on live things like crickets, grasshoppers, or things that are very ephemeral, like it's a couple of seeds, but someone else, like another ant, could come by and steal those seeds. So it could be changing. The feeder quality could be rapidly changing. They have a high epsilon, so they're not very good trail followers. And that represents, if we're going to model them as one of these epsilon greedy policies, then a different balance between that old information and new information. And that has to do with predictability. So if you have a high epsilon, then there's a good chance that you think that your reward is very variable. If you have a low epsilon, then you think the reward is constant, and you just need to figure out what the reward is. So this is one way we can do our searches. And we have this epsilon parameter, which reflects our prior information about how ephemeral, how volatile the rewards are. Alternatively, another common way to do this search is a softmax policy. So we've talked about softmax. So this epsilon greedy policy, it's you pick the max most of the time, and then everything else at random. And so, but you don't care about how, who's second best. You only really order things to say who's first, and everybody else is the same. In a softmax policy, you draw from a Boltzmann distribution. So you have these qualities, which are not probabilities, but if we put them into the Boltzmann, then it pops out probabilities. And so then now we can say, based on the relative qualities, we're going to get a probability distribution. Maybe it'll be 60% the max, 40% the second, and then nothing else left over for the third, maybe 60, 35, 5. And so then we just draw from the Boltzmann distribution, and then that way we're more spread out. Now, just like there's the epsilon parameter for the epsilon greedy, what's the parameter we have in the Boltzmann? Anybody remember? What changes the flatness of the Boltzmann? Or softmax? Starts with a T, ends with a chir. Anybody? Yes.
Temperature?
Temperature. So hidden in here is that we also have a temperature parameter. And so just like you can, based on how ephemeral you think things are, if you think things are rapidly changing, you then, when you set up your search strategy or exploration strategy, you can set this as a very high temperature, which means it's almost going to ignore the relative qualities and it's just going to go anywhere. But if you set it to a low temperature, then you're going to say, I really trust the rewards. I trust the prior information. I trust the old data, the predictions. And I want you to go most of the time to the places where you have the maximum. And so that temperature parameter allows you to say, how much do you trust the maximum and how much do you really want to spread things out? So two very similar approaches. They just sort of have a slightly different shape in the distributions that they put together. So those are our exploration steps. And again, this is like ants balancing social old and private new information. All right, so once we've gathered information, now we need to update our quality estimates. This could happen in the head of an individual, or in the ant colony, it could happen by laying pheromone in space. So how you implement this update rule, there's a variety of different options, but this general update step is, it ends up being how we kind of model things from time to time. So the idea here is that we have a quality value from the previous step, and we would like to generate a quality the next time step using information that we have just acquired. So we've got our reward that we got from our current action at our current state, and we have our current estimate of quality at this state with our action that we just took. And then this reward that we got, well, there's this, and this, I'll get rid of this tape here, sorry. But we have this guy right here. We know we've moved to state S prime. And so we can think ahead, we can do this temporal discounting, where we could say, okay, my reward for taking this action is not only the instantaneous reward that I just received, but it's also, because I'm thinking about accumulated rewards, the discounted, time discounted rewards that I'm going to get from the next actions that I'm going to take. So I have a quality which represents actions I take here, but then when I take an action, I move to a new state and I'm going to take actions there. So that's what this is all about. It's saying at my new state, I'm going to maximize over the actions available at that new state. And I'm going to say, I imagine that I then took that best action there. And then I'm going to discount this with this parameter, which is a little bit like, and we're going to go into where this comes from, but it's a little bit like an interest rate at a bank. It's like you value things more now than you do later, but you do value when you get stuff later. So if you have the money, you'd like to spend it now, but if you give it a good enough interest rate, then you're willing to hold off and spend it later, because later they'll give you more money. That's the interest rate. So there's a similar idea here of this discount rate of, how much value do you get? So another way to say that is I could spend $10 now, or I could spend $10 in a month. And I will get a reward from spending $10 in a month, but I've lost out on whatever that benefit was for the whole month that I was waiting. That's the discount rate. And how do we set that discount rate? We're going to get into that in just a second. But that's basically the update rule here. So I've got my old estimate. So this here is meant to look like a difference. This is basically what I thought QSA was. And this is my new estimate of what QSA actually is. Because it's that new reward that I just received, plus this additional reward I'm going to get in the future from taking an action at the next step. So this is sort of the idealized update of QSA. Like, you know, this is, if we didn't have noisy estimates, this would sort of be what QSA should be. And this is what I thought it was. And this is the difference between what I've experienced and what I thought before. So that tells me what amount I should, or what direction I should move in if I'm updating my estimate of QSA. So if I've got noise and, you know, I can't just immediately, like if I set alpha equal, if I set this learning rate equal to 1, so that ends up dropping all this way, then this QSA cancels with this QSA, and I say my next QSA is just directly equal to this. But I don't trust that this reward is 100% informative. So to be conservative, I set this alpha to something that is less than 1. I set it to something small. It's a step size. So I'm saying that right now, based on the reward that I got and my estimate of the rewards I'm going to get in the future, then I'm estimating the reward that I get from this point right here, S, for doing action A, is probably, you know, I'm probably underestimating it. So if that's positive, the actual reward is over there. So I would like to increase the value of doing A at state S. But I don't trust this 100%. So I just know that it's greater, so I'm just going to take a little step. So if I completely trusted the reward I would get, I would walk my estimate way over here. But instead, I'm going to walk my estimate of the value just a little bit in that direction. And then if I do that over and over again, I can hopefully converge on a good estimate for QSA. So that's kind of what I think I'm trying to summarize here, is that I'm gradually adjusting QSA toward its true value by getting noisy estimates of rewards from the actions that I'm taking. And this is a form of what's called temporal difference learning. So this is the old value, this is the new value, this is the learning rate. So in general, if you've got a current state and a next state, and you're trying to learn the value of your states, then this temporal difference learning is a way that as you keep moving from state to state, using the value experience at the next state minus the value experience of the previous state to try to update the value of your previous state. That's what's going on here. So this is a subset of TD learning, Q learning. Any questions about that update formula? So, you know, if you're just an old school computer, you can just implement this like in a line of code. But you can also imagine modeling the deposition and decay of pheromones in this way too. So with a little bit of rearrangement, I hope you can see that, you know, I've got like this QSA. If I factor the QSAs out, then I get effectively a decay of QSA, like this QSA minus this QSA with this alpha, it effectively sets a decay rate. So I'm getting deposition from my new ants, I'm getting decay from my old. So I could just as well model the deposition of pheromones and the decay of pheromones as a Q learning update rule. So that's why we're thinking of ants as just doing Q learning in a distributed framework. All right, questions about that? Okay, so here's the one direct connection to neural networks, deep Q learning. So this Q function is just a function. It's just a parametric function. So if it's a really, really big state action space, like lots of states and lots of potential actions, then rather than coming up with some like long arithmetic formula, I could just implement my Q as a neural network. So the idea here is I can take my update rule. This is just a copy and paste of the update rule from the previous page. I don't know why I taped over it. And so that's our normal update rule. And the idea here is I'm just going to take a deep neural network. So now I've got theta. Theta are my weights of my neural network. So I'm just going to I'm going to do function approximation of QSA with a neural network with these weights. And now I just need to turn my update rule there, this normal update rule, into something that can train these weights. And that's relatively easy to do. I can create a loss function. I'll just get rid of the suspense. I can create a loss function which takes my previous estimate of quality, and it takes my updated estimate of quality based on the actions I've taken, and it tries to bring these two close together. And so I just take this and I say I want to bring that to 0. So I'm going to take this difference, square it, and then I'm going to treat that as a loss function that I can then use with backpropagation. Now there's one little cute wrinkle here, is that this here is playing the role of, if I'm doing supervised learning, I've got the evaluation from my neural network, which this is playing the role of that. And then I've got a target, which comes from my data. And that's what's playing the role here. So what we're going to do is freeze the weights of our neural network and treat that as kind of ground truth. And we're going to freeze them for every few hundred or thousand updates. And so you have your neural network and it's sort of modeling you kind of use your old information to try to model where you want your neural network to go based on the rewards you're getting. And then over time, as this thing updates, then these weights start, you kind of latch those new weights in, and then this gets updated too. And this, you want to put a little bit of a time between theta and theta minus, the frozen theta, just to prevent things from kind of chasing their own tail. And so experience kind of shows that's why you kind of need to sort of freeze this target over here in order to make this work. But it's just, and it's just a little bit outside of the scope of the class, but what I'm just trying to say here is that you can use good old-fashioned backpropagation with supervised learning, and as you're moving through the space, you're generating a training data set for good old-fashioned supervised learning using a simple loss function and backpropagation. And then that is another way to update this. And this is a so-called deep Q network, a DQN, or deep Q learning. So all deep Q learning is just Q learning, where your Q function is a neural network, a deep neural network that you then update with backprop. So that is our direct tie to Q learning. Otherwise, everything else I'm about to say could apply to reinforcement learning implemented with any substrate. It doesn't have to be a neural network. Questions about that? Okay. So where the heck does this discount rate come from? And so now we're going to go back to biology and optimal foraging theory. So this is the picture we have. We have an animal moving through a forest. It has a bunch of distance between patches, like little shrubs that actually have like food in them. And so as you go to the shrub, you pick out berries. And initially you see a lot of berries. And so you're picking out the berries at a high rate. But eventually this shrub's berry count goes down and it's really hard to find the next berry. Now you could deplete the whole shrub of berries, or at some point you could go looking for the next shrub. Because the next shrub, it's really easy to find the berries. If you don't like the foraging example, let's say you've got an electric car and you need to decide when to leave, like you've got on a long trip and you stopped at a place to charge your electric car. You could charge the battery up to 100%, but whereas going from 0 to 80% to like maybe 10 minutes or something like that, going from 80% to 100% will take another 45. And so do you bother charging all the way up to 100%, or you just stop early at 80% and then drive on and then stop at the next station? And maybe you'll stop at the next station that is a little bit closer than you would if you went to 100%. But if you're only spending 10 minutes every station, as opposed to spending an hour at every station, then overall you get better value. What I'm trying to talk about here is that there are local benefits and then there are opportunity costs. And the idea that we're going to try to capture here is that you decide how much local benefits you want based on your opportunity costs. In the case of the forager moving through the forest, how spaced apart those shrubs are is going to determine how long they should stay in each individual one. In the electric car example, how far apart charging stations are is going to determine how long you're willing to stay at each charging station. So there's an opportunity cost to, well, you know, I could stay here, or I could be searching for the next reward opportunity. And searching for the next reward opportunity means not receiving a reward. But if I find the next reward opportunity relatively quickly, then I can start receiving reward much more quickly at a higher rate than I can if I stay where I currently am. So that's what I'm trying to motivate here. So I'll try to formalize that right here. So this is the idea. We've got this forager, and she encounters this shrub, and this shrub has a certain average net reward from that patch. I'm going to call these, whenever we talk about in biology, whenever you talk about a prey item that is a lumped prey item, you eat and you get the whole thing, they just refer to that as prey. But if you go to an area where the longer you eat, the more you get, and you can stop early, they refer to that as a patch. So this patch has this ability that you theoretically could eat the whole patch and get this much gain, this many calories out of it. But you can stop early and get less calories, but you get to stop at a different sort of rate of gain. So the longer you stay, you get diminishing marginal returns. So the slope of this, it decelerates. So initially you have a high slope, and then eventually you have a very flat slope. So the idea here is that you have to decide when to leave. This is probably too early because you didn't accumulate a lot of calories. And so the time in between patches, you're probably going to use up the few calories that you built up. This is probably too late because every minute that you stay in this patch, you're not really getting that many more calories. And that minute might be better used searching for a new patch that's not depleted. So there's probably some intermediate, just right time in that patch that is the optimal patch leaving rule. And the question is, how do you determine that time? So, and like I said, because other patches exist, there is a so-called opportunity cost of staying too late. So that's the model that we're setting up that we're about to solve here. And then this will give us meaning to where that discount rate comes from in reinforcement learning. So any questions about this setup? We got patches that you can eat from and leave early, but the later you leave, the fewer returns you get every second you stay in the patch. The earlier you leave, the less gain that you have from that patch. So there's a trade-off. Okay, so we're going to add a few more variables here. We encounter the patches at a rate lambda, encounters per second. And the patches yield, as we said before, an average g tau value for t tau time spent in them. And our goal is to maximize the long-term rate of gain. Those of you who are interested in stochastic modeling might recognize this as a Markov reward renewal process or renewal reward process. If you don't understand what that means, that's totally fine. Famous result in renewal reward processes is that if you want to maximize this value here, so this is the gain over time, the gain accumulated over your total foraging time. If this is the currency, you want to maximize this limit, then you end up getting, and I'll define this down here, but it ends up basically being the expected gain you get from one renewal cycle, one patch, divided by the time it took for you to find that patch plus the time in that patch. And so we'll see that here. Now you might say, why do I pick this particular reward function? And at least in biology, this ends up being argued that you know, so they say in like behavioral ecology, there's the 4 F's that animals have to worry about: foraging, fighting, fleeing, and reproduction. And so foraging is one of those. The other 3 is other stuff you got to do with your time. And so if you just maximize the calories you get back from foraging, then that's great. That's just maximizing the numerator G. But that strategy may leave you no time to do anything else. So at least in biology, there's a thought that it's a multi-objective problem, that you can maximize gain at the minimum time. So you want to say, I need to get the best rate out from my foraging. And that's the reason why this is the currency. Now you can set this up as a multi-objective problem where you want to simultaneously maximize G and minimize T. And it just so happens that the people who came up with this so-called marginal value theorem, they didn't do it that way. But if you do it that way, you get the exact same result. So this is our reward that we want to maximize. So what do? Well, and yeah, this is, I'm just saying that the numerator here is the average gain and the denominator average time from searching and processing one patch. That's where this comes from. So that's just sort of the famous result from a renewal reward theory, is that if you want to do that, it just reduces to that. So now we just said that in order to maximize R, I don't have to worry about this limit anymore. I just maximize this thing. And that's pretty easy to do. We're going to take the partial derivative of that thing with respect to the average time in the patch. So quotient rule, bring the denominator up, take the derivative of the numerator, subtract the numerator, derivative of the denominator, divided by the denominator squared. If I want to figure out my maximum, the optimal time in the patch, I set that thing equal to 0. Setting that thing equal to 0 means ignoring the denominator, which is always positive, and basically setting these two things equal to each other. But if I set these two components of the numerator equal to each other, I get this nice result, the so-called marginal value theorem, which I'm going to graph here in a second, and it'll be, I think, even nicer. I basically get that the instantaneous gain rate of change, the instantaneous rate of change in the patch is equal to, we get the same formula out. We get this out. So we stay in the patch until the instantaneous rewards, rate of rewards in the patch falls to the long-term rate of rewards. That's what this thing says here. I could even call this R star, I guess, because I'm using it with this star relates to that star there. So when that condition holds, so as we'll see here in a graph in a second, we're going to enter the patch, and these instantaneous rewards are high. They're higher than the reward we're getting from the environment as a whole. So this is the average sort of exchange rate between time and calories from the whole environment. So me just living, this is how much energy I'm getting per unit time from all of my foraging activities. And this is how much energy I'm getting per unit time from this particular patch. So long as I'm getting more energy per unit time from this patch, I stay in the patch. At the point where my energy per unit time drops to my long-term rate of gain, then I leave the patch. That's what the marginal value theorem is saying. Now let's see what that looks like in a graph. So here is the marginal value theorem, and I'm going to plot for one patch. And I'm going to plot my gain in that patch the same way I did before. I made it maybe a little cleaner looking, but it's the same curve. And we can generalize this to multiple patches, but I'm just going to do it with one patch type. So there's multiple patches, but they're all of the same type. And so I'm going to plot 1 over lambda, which is the average time between patches. Before I write that in, all right, I'll just write it in over here to emphasize this. So this here is the average time between
patches. So it's our average search time. So if I look at all of this together, what I've got here is that this graph that I've plotted here, I just plotted the gain from one patch. And then I just decided, I'll just say this, that on the negative time, to plot the average time between patches. And you say, well, why did I do that? Well, the geometry will show why I did that in just a second. If I then anchor a door, you know, this giant door that I just let swing down and hit this thing and rest there. If that's anchored here, if it's got a hinge here, and it comes to rest on top of here at this point of tangency, then what do we know? Well, the slope of this line is rise over run. The slope of this line is the long-term rate of reward. So the slope of this line is the gain that I get at this particular time, divided by the time I spend in the patch, plus the time that is in between the patches. And that's what I have right here. So that's this slope of this line right there. But I know that because it's at a point of tangency with this curve, that's also the point of the instantaneous rate of gain at that patch leading time. So this is a graphical representation of this expression. And that allows us to give a nice conceptual model for what happens when we change the time in between the patches. So, and that's what's going to be spelled out down here. So what we're saying here is that we leave, as I said on the previous slide, leave when the instantaneous rate of reward falls to the long-term rate of gain. And so what that tells us is that if we increase the time between patches, what that's going to do is that's going to put this anchor point farther over. So if I were to draw another one of these lines, it would intersect up here. So that would increase my time in the patches. If alternatively, I shortened the time between patches, I made the whole environment richer, then now that line would be anchored closer and its point of tangency will have a shorter patch residence time. So this result, which every junior in biology learns and then forgets, is the conceptual model for how we think about how animals make this decision. And so, I mean, those of us who are used to looking at functions, you'd say, that made sense to me when I looked at this. But at least plotting it like this is a better way to communicate those ideas. It's very economical. Like the economics people love to have these cutesy little graphical representations of these expressions, and that's just sort of one example. So, but I think it's kind of elegant. This cute idea that if I move this way, then I'm going to move the patch residence time this way. And then the more general idea here is if I enrich the environment, I spend less time in each individual investment. If I make the environment poorer, then I'm going to spend more time in each individual investment. Another way to think about this is interest rates at the bank. Is that if I move this line over, it makes this slope steeper. What that effectively does is it means I get more interest out of the bank. That if I put my money in the bank, it's going to earn more. So that means that anything else that I do, I'm going to do less of because I need to get the same rate of return I get at the bank. So I have this in my non-bank investment. I got my stocks over here. I could be putting money into my stocks, but if the bank gives me a higher rate of return, I'm going to put less money in my stocks and more money into the bank. But if the bank's interest rate goes down, so if now this slope goes down because now there's more space in between the patches, the interest rate I get automatically from the bank goes down. So in that case, I'm going to put more of my money into stocks because now I can tolerate my stocks doing a little more poorly because they're still going to do a lot better than the bank. So this is how animals invest their money. They get an interest rate from the environment, and then they have to decide, are they going to invest in search, putting their money in the bank, or are they going to invest in the patch? Are they going to invest in exploration or exploitation? This is the natural bank. Capital assets for animals. And this R star, this interest rate that I talked about, this is our opportunity cost. And this is the temporal discounting factor that you use inside your Q-learning update rule. So when you're setting this hyperparameter, you have to think about how rich do I think this environment is? And you might have an agent that tries to estimate the richness of its environment and then update this dynamically based on that. And that's effectively what animals do, because if they're sensitive to the rate of return that they're getting back from the whole environment, they're effectively sensitive to gamma. They are detecting this interest rate and adjusting their decisions based on this interest rate that they experience. So that's where the discount rate comes from. Questions about that? And this is the marginal value theorem from Eric Charnov, I think 1976. Charnov was a faculty member at University of Arizona for a long time, I think. So it's around here, retired now. Okay. All right, so now what about exploration strategy or this epsilon? I've already kind of hinted at this, but animals dynamically shift between exploration and exploitation, and the reward variability, it seems to be important. So I've mentioned a couple of examples already. Here's another one. Bees that discover flowers. So they go to a flower, they get a bunch of nectar, and there's a lot of flowers around. So then they will continue to exploit that nectar. So they have a low epsilon. So at that point, they focus on that nectar. But eventually, once depleted, then they stop coming to that flower. And we model that as they then flip from exploitation back to exploration. And so that's one example of it. So if how might you do this as a robot or another artificial agent? And there are a couple different ways to do it. One of them is schedule based, and you can think of this. It actually looks almost identical to simulated annealing. So one of the ways you do this in reinforcement learning is I'm going to start with a high temperature. Literally, in that if you're using softmax instead of epsilon greedy, then you just say, I'm going to start at a high temperature, just like simulated annealing. And then over time, I'm going to cool the temperature. So I'm going to start with exploration, and I'm going to finish in exploitation. So that's one way to do it. But then you have to struggle with, how do I set that schedule? How quickly do I decrease that? So a more dynamic way is to be like the bees. And if you get a high reward over and over again, then you crank your epsilon down, you crank your temperature down, and you keep doing what you're doing. But when you keep doing that action, if that reward, that little R, starts adding variability, then you match that variability you get to that epsilon. And so you kind of get a epsilon variability matching, where the larger the variability, the larger the epsilon. And so this way is an easy way to use the environment to determine how often you should trust your past information. And so it's like once bitten, twice shy. So if you go back to a site that you were convinced had good reward and it has no reward or it's punishing, then you stop paying attention to your history and you say, you just do new things. But if you go back and you keep getting the same reward over and over again, then you just keep going back. All right, so that's the exploration. So we've done the updating and the exploration. Questions about that? Okay. All right, so outcomes of Q-learning. I mentioned the matching law already. So I've said, as in psychology, the time or frequency spent on each essay pair will be proportional to the corresponding reward rates. So if you know that when I was at this state, I did this action, I got a high reward. When I was at this state, I did this action, I got a low reward. If I got a reward in both, I'm going to try to spend some of my time here and some of my time there doing this action and that action, but I'm going to spend more time where I got the highest reward. That's the so-called matching law. And you do, if you've got a good search strategy, a good exploration strategy, and you've got fast and accurate queue update rule, then you will achieve matching, just like you do in psychology. And so now, what's kind of cool is what if you have multiple queue learners in the same space? And then you get the ideal free distribution, which is another social foraging idea from biology. So the ideal free distribution, this is the ducks on a pond model. So, you know, if you have 3 people standing around a pond and they're throwing out breadcrumbs, and then they have an infinite number of breadcrumbs, but somebody's throwing out once per second, the others are throwing it out, 5 times per second. I think really fast, maybe maybe I'll go the other way. Once per second is fast, and we'll say that, this one is once per 10 seconds, and this is once per 30 seconds. Then you start noticing that the ducks will achieve a stable distribution where you'll get more ducks around the once per second than the once per 10 than the once per 30. And that's the so-called ideal free distribution. So the idea here is that the agents are free to move to any patch. There is a generalized version of this called the ideal despotic distribution, where agents can prevent other agents from joining. But in this case, they're free to move anywhere. But when they move into a new patch, they deplete the reward rate of existing agents that are also there. So there is a social coupling. This is a scramble competition, an interference competition, where there's one reward rate for all the ducks, and it's a little bit like fitness sharing. And once a new one comes in, then that reward gets divided by how many ducks are there. And so each duck is running a little reinforcement learning, deciding, does it go, does it move here, there, or there? And so, in other words, you can think of it as the states are the locations of the pond, the actions are, do I stay or do I leave? So at this location, based on the current rewards, I'm going to stay. At this location, based on the current rewards, I'm going to leave. All right, so the outcome is the allocation in space where all learners will end up getting the same reward. So you're going to see, 100 ducks here, 50 ducks there, 20 ducks there. Every individual duck is actually going to be experiencing the same reward rate. But the different numbers of ducks will reflect the different amount of reward going into the group. But each individual ends up coming to an equilibrium, which is a Nash equilibrium. So that the pond thing is that at equilibrium, every duck it's better for them to just stay where they are, because if they move to another patch, all of the ducks there are doing just as well as them here. So if they move to another patch, it's going to benefit the ducks they leave behind, and it's going to hurt them, because now they'll get a smaller share, because every duck before them was getting their share, and now that they've joined, they have to get a smaller share. So it's a Nash equilibrium, this ideal free distribution. The other cool thing about it, and I'll plot these in a second, is it actually is not only a Nash equilibrium, but it is a form of Pareto equilibrium as well. So it actually maximizes the exploitation of the environment. So this ideal free distribution is not only the best thing each duck can do without collaborating with another duck, but it actually maximizes the use of those breadcrumbs. So all other distributions would end up getting an accumulation of wasted breadcrumbs in an area, and ducks not getting enough. You'd have starving ducks in one patch and rotting breadcrumbs in another. This way, you actually get a matching. By matching the reward, the supply and demand, you actually maximize the exploitation of that reward, which I think is kind of cool. The way we usually plot this is with suitability functions. So the idea here is that each patch, these are different points on the pond. This is the reward rate per individual. So if there's no individuals at patch 1, they get a very high reward. If there's no individuals at patch 2, the first individual gets a moderate reward. If there's no individuals at patch 3, the first individual gets a low reward, relatively low. relative to the others. As one duck moves into patch 1, the marginal reward to the next duck moves down. As a second duck moves in, the marginal reward moves down until eventually it's equal to the entry reward at patch 2. At that point, the next duck could join patch 2 or patch 3, it doesn't matter. So let's say they go to patch 2. Well, then patch 2 will go down. The next duck will go back to patch 1, patch 1 will go down. And then the two of them end up kind of going back and forth until they hit this point at patch 3, where now it's best to join patch 3. So as you keep pulling in more ducks, what you get is you get a truncation of these two as everyone fills 1. Once 1 is depleted enough, then you get a truncation of 3, but you start getting ducks residing in 2 and 1 simultaneously. And then eventually you turn on 3 and eventually get ducks across all 3. So at this population, I'll say a population of n ducks, you get an equilibrium, which we draw a straight line across. And so in order to figure out your equilibrium, you draw your suitability functions, and then you just take a horizontal line. Of course, there's an analytical way to do this too, but graphically, you take a horizontal line and you move it down, and then you see where it intersects with all of these, and you get intersection points down here. And then you add those up together. And when that hits your population size, that is your equilibrium distribution. And every individual duck gets the same reward, but the number of ducks is the matching law, is the psychology matching law, where you get more ducks at the patch that started out with a higher reward rate in total, and less ducks at the one with the lower reward rate in total. That is our social matching law, the so-called ideal free distribution. And if you distribute a bunch of robots on that pond that are just looking out for themselves, they're not paying attention to the other robots, only their local reward rate, they too will reach the ideal free distribution. So questions about that? I've had colleagues that use the IFD in municipal water control, for example, deciding which water goes to which part in the city. We've used it to distribute robots around search areas, just in a decentralized way. So rather than trying to say, I need 5 robots there, 2 robots there, 1 robot there, that we sort of, this is a way to load balance, where every robot pays attention only to its own reward. And because that reward gets depleted by other robots, then robots just start leaving an area that if they're not getting enough reward, and they self-allocate to a distribution, which is Pareto optimal, which is actually good for everybody. It's globally optimal, it's maximizing our coverage of the area based on pop-up rates. So that's ways in which we use that. Which, you know, can be cast as just another application of reinforcement learning. Okay. So that's basically what I've got for you. So it's, you know, just saying that reinforcement learning you can view as the machine version of operant conditioning. We have ant pheromone trails. Those trails themselves are a type of distributed cue learning where the network of trails is like a distributed cue network, you know, so it's, instead of being a neural network, it's a pheromone network, but it's capturing the same information. So, you know, we could also implement that with an actual neural network. That's DQN, or, you know, deep Q learning. So I'll write DQ in there. That update rule that we talk about has this funny discount rate. What is that discount rate? Well, that is the long-term rate of gain you get from other activities. It's basically the time value of money. And the marginal value theorem from biology, I think, provides a nice interpretation of where that comes from. You know, exploration can be tuned dynamically based on reward volatility. And if we have distributed reinforcement learning, one of the nice results is even though you don't have them agents talking to each other, which there are reinforcement learning where agents talk to each other. There's a bunch of multi-agent reinforcement learning, or MARL, where agents base their rewards not only on what's going on currently, but others. Bacterial foraging optimization, for example, you could view that as a case of multi-agent reinforcement learning. But if you have the simplest distributed reinforcement learning, where agents don't pay attention to other agents, but they feel the presence of other agents on their diminished reward, you'll get an ideal free distribution. And that ideal free distribution is both Nash optimal and Pareto optimal, which makes it a very useful design tool. And so this is a cool emergent collective pattern. So with that, next time we're going to shift then to self and unsupervised learning, where we get rid of all the rewards, and still we get agents that learn from the environment despite not having any rewards. And then that'll finally allow us to close with getting back to spiking neural networks, which are really good at unsupervised learning, and what those devices look like and what we can do with it. So any questions? In that case, your reward for the reinforcement learning lecture is we get out of it.